Last time, we talked through a simple example of replacement analysis where we had the choice of either replacing something now or replacing it 5 years into the future. However, we also introduced the concept of an economic lifetime, which is the time that minimizes the annualized cost of operating a piece of equipment. That means that in theory, we shouldn't just have a one or the other decision to make about replacement. We should be thinking not of do we replace it now or at some fixed point in the future, but we should be thinking of when should we replace this equipment on a continuous spectrum. So anytime between now and 5 years from now. The intuition behind this is that if we add a year to the lifetime of an asset, it's reducing the annual worth of the initial capital cost by spreading it out over a longer time period. It's reducing the market value at which an asset could be sold, and it's also typically going to increase the annual O&M expenses associated with keeping it functioning. Therefore, the expected uniform annual cost, or EUAC, is going to vary with the choice of lifetime. Ideally, because the firm wants to minimize their costs, they want to only use an asset for its economic lifetime and no longer. Can you think of a reason why, though, a company might sometimes continue operating equipment past its own economic lifetime? Take a moment to think about it and then continue on. Did you pause it? I'm watching. Sometimes a company might have to continue using something beyond its economic lifetime if it simply doesn't have a more economically attractive alternative. Remember that project selection is always a comparative exercise, and so in isolation, we might want to only use something for its economic lifetime and then potentially replace it with itself. But what if the project's not repeatable? In this video, we'll talk about how to calculate the EUAC mathematically and the economic lifetime, and then how to apply it in a project selection context to problems like this. First, though, let me ask two questions that motivate the parameters for how we're going to actually define the economic lifetime mathematically. First, why do we need to use the average annual worth as opposed to calculating a present or future worth as a function of time? When we allow the lifetime to vary, putting things on an annual basis is what allows us to make an apples-to-apples comparison. We want to be able to say, this project costs so much per year. Next, why do we only look at the annual worth of costs instead of both cost and benefits? All this is doing is simplifying the process and restricting ourselves to a situation where the alternative challengers that we could replace the Defender with are providing the same benefits. So therefore, if we're focusing on the differences between projects and the benefits are the same, then we just look at the costs. Keep in mind that the expected uniform annual cost is really just a fancy way of saying the annual worth of the costs of a project. So we can think about it in two different ways and calculate it in those two different ways, but we're really just taking the annual worth of costs. So the direct method, what we're going to do is, given a particular choice of lifetime K, we're going to start with a cash flow diagram or just a breakdown of the cost per year. We're not going to assume that the costs are the same every year. And then we'll look at an initial investment at t equals 0, or the current time, a market value at the end of year K equal to MV sub K, and then expenses E sub J in each year. If that's the case, then our EUAC is just the present worth of all of the costs from now until time t equals K times an A given P factor. That's all we're really doing. We're going to take the present worth of all of the costs, and then we're going to spread it out over K years using that A given P factor. So our present worth in general terms, is going to be that initial investment minus the market value at time t equals k times a p given f factor to bring it back from k to 0. And then we're going to add all of the expenses from time t equals 1 to t equals k, but we're just going to discount each one as we go a different number of years. So E sub 1, the expenses in the first year, is going to get multiplied by P given F for 1 year, E sub 2 times P given F for 2 years, and so on. The marginal method is a little bit more complicated, but it's useful if we've already calculated the EAC for a previous time period and just want to know how to adjust it in order to calculate the EAC if we add another year. What this assumes is that we know something called a total marginal cost for each year, and that's what we have to calculate. It's the increase in the total project cost from extending the lifetime one more year. So this total marginal cost associated with year K is expressed in terms of a future worth in year K. That's what we're going to need in order for the formula that I'll show you to work. The type of question where this is useful is if we already know what an average cost is over a period of, say, 9 years, then we know that cost in year 10, so how do we calculate what the average cost would be over the whole 10 years? If we were going to do this intuitively without taking account of discounting, we would just start with our average cost over 9 years, multiply it by 9 to get the total cost over 9 years, add the cost in year 10, and then divide by 10 to get an average cost over 10 years. We're going to do something really similar to that. We just have to account for discounting. We're going to start with the EUAC over k minus 1 years, which is an annual worth, and we're going to convert it to a present worth using a p given a factor for k minus 1 years. Then we'll add the present worth of the total marginal cost for year k, which is Tc sub k times a p given f factor for k years. Then we convert all of that, because now it's expressed in present worth terms, back to an annual worth using an a given p factor for k years. And that will give us the EUAC at year k. That assumed that we know what the total marginal cost is in future worth terms for year k. So now we need to think about how do we calculate that. There are a couple of different things that go on when we extend the lifetime of a project from k minus 1 years to k. The first thing is that the market value is going to change from mv sub k minus 1 to mv sub k. The next thing is that we get another year of expenses, E sub k, and then this is the tricky part. There's an opportunity cost associated with waiting another year before selling. In other words, if we had sold the asset in year k minus 1, then not only would we get the market value, mv sub k minus 1, then as we go another additional year to year k, we could earn interest on that value. So we could have taken mv times k minus 1, invested it, and earned I times that over that year. So those are the three different things that change as we go from k minus 1 to k. And so therefore, our equation for the total marginal cost associated with year k is going to be the difference in market value between k minus 1 and k, add on the interest associated with mv sub k minus 1, that's our opportunity cost, and then add the additional expenses. That allows us to also calculate the EUAC from only using the total marginal costs. We can start in year 1, calculate the total marginal cost associated with going from t equals 0 to t equals 1, and so on, each time converting it to a present value. And then once we add those all up using that summation, then we just convert it back to an annual worth using an a given p factor. The total marginal costs associated with each additional year of lifetime are expressed in future terms, but each in a different future year, so we need to convert them all to present worths in order to get a common base year. After summing them up, they're still in present worth terms, so we need to convert them back to an annual basis in order to get the EUAC. That's how you can think about interpreting that equation. In the next video, I'll talk a little bit more about the intuition behind how the EUAC changes over time, and then work an example to illustrate how we find the economic lifetime.